Welcome to the talk, everyone. I have a quite broad topic, so the way I'm going to do it, I'm going to walk through the steps of the presentation briefly, and in the end there will be plenty of time, hopefully, for a Q&A, so we can dive into specific topics, the topics that you feel are most important. My name is Remi. I'm the research engineer behind a Norwegian site called utdanning.no. It's the official Norwegian site for education and career data. We are owned, or I work for, the Norwegian Center for ICT in Education. It's a national center, so I work for the government. We run Drupal and Solar 3.6. We have roughly 3 million visitors a year. Our Solar index comprises of about 12,000 documents and 18 million terms, divided in roughly 260 fields. So it's not a huge index. We focus on quality. Quantity isn't really an issue for us, nor is latency. As you can see from our latency, it's like 8 milliseconds average. It's not a problem. We have only 1 query per second at peak times during normal days. And we have around like 9 million searches a year towards our Solar server. So our problem is not about data quantity, but about data quality and how to search that data efficiently. Because we gather data from several official sources. We transform and normalize them, depicted by the black box. I won't talk about the black box. Just know that it happens. We get very structured data in. We put it all into Drupal, where it's nicely formatted in an entity and relationship model. Then we have an editorial staff, which adds value to what we fetched from around. And also they do write-ups about professions. They write interviews. They make like educational summaries and stuff like that. So all this adds value to the data we fetch automatically and semi-automatically. So what I'm going to focus on is the Drupal part and how we get our data into Solar. And after that, how we search that data. So first is the indexing. We have all data structured in Drupal. That's not a very good match for the way it should be in Solar, because in Solar it's good to denormalize for search speeds later on. So for that, there is a great module for Drupal. For those of you that use Drupal, I recommend using that module. It's called Apache Solar Search Integration. I think it's in version 7x12 now, but anyway. The module provides basic Drupal integration. So it tracks document changes in Drupal. So if you add a document, edit a document, delete a document, it will keep track of that and then send it in batches for indexing into Solar. So it will take care of all that kind of issues. You don't have to think about it. It has some facet support. It does full text search well, of course. But above all, it's very easily extendable. That's why we use it. Because, for instance, it lacks deep introspection of Drupal entities, so you can't really denormalize the data in a useful way, the way we need it anyway. And the hierarchies are really hacky, but that's a Drupal thing. Like multiple parent hierarchies, they really don't work, so you have to write that part yourself. On a side note, the module also requires you to put some special configuration files in the config directory of your Solar installation for it to work correctly. It's got mostly to do with dynamic fields and stuff like that in order for it to translate the Drupal schema into a Solar schema. So based on that module, we extended it quite heavily. We added deep introspecting capabilities. So you have a node which is related to another node. We gather data from the other node and index it with the parent node. That's what we mean by deep introspecting. That way, we do data denormalization. We added a solid hierarchy support for us to be able to do hierarchy facets. We had to add some pivot facet support. We're on Drupal, Solar 3.6, so pivot faceting isn't the real part of the Solar framework yet. We added atomization. There is a Drupal module called Atom. It will atomize a single document. I'll tell you later why we do that. But we store actually an atomized version of the Drupal nodes in Solar. We also added some other stuff, changed the configuration files slightly to be able to do autocomplete lookups, and did some copy field stuff that you do in schema XML files. So basically, we have things in the Drupal database normalized, and we flatten it and duplicate data and put it into Solr because space isn't an issue for us. Storage capacity is not an issue. We want speed. So here's an example of the Acme University. This is how this is a mock-up document, Solr document, of course, depicting one organization. You can see it from under the array with the related nodes. That's an example on how we flatten data. We put all the study programs offered by a specific organization and index it together with it so that if you search for Acme Rocket Science or only Rocket Science, the Acme University will show up. It's a basic example on how you do data denormalization. Further down, you have the geography hierarchy facets, not the facet, but the fields, which you can facet on later. And you can see how we solve the multiple parent hierarchy problem with prefixing all the fields, the values in the hierarchy field with 1, 2, 3 based on which level it is. This way, you can use the facet prefix technique to do hierarchic facets. More on that later. And the last part is how we solve the pivot faceting problem. I'll come back to that as well. This is an example of a course that we have indexed. And here we have also flattened or duplicated data slightly, telling which university offers the course. So if you search for Acme University, you will get all the courses that are offered by Acme University, even though it isn't there originally in the normalized data in Drupal. So now we have indexed our data. We have normalized it. We have tweaked and massaged the data in order to be able to do efficient search the way we need it. So we have 3 ways of searching our website. We have the site search. It's a classic site search that our visitors use to find their way around. We have embedded search. We offer for external parties to use our web search directly. And we use the feeds engine that's actually powered by Solr. I'll go briefly through all these 3 ways of searching our site now. So first, the site search. Our goal is, of course, to make people able to find what we have at our site. So to do that, and this you won't probably hear many people at this conference say, but to do that, first you have to know your user. We have a very domain-specific website, educational data. So we have to know the user. We do interaction design, we do user testing, more interaction design, user testing, and then when we're happy with what the users tell us, then we put the graphical design. So the graphical design is there, and then we have a GUI specification that we must implement. That was the way we did it anyway. And with that GUI specification, it came clear to us that we needed Ajax, because we have like a variety of facets and full text search on one page, and for each time a user clicks on a facet, you don't want him to reload the whole page over again. So we used Ajax Solr as our JavaScript framework to get that Ajax capability. The link there, or you can Google it. It refers to a tutorial, which is great. It will manage all the querying for you. It has some basic widgets prepared already for you, and well, it's really efficient. You do one query, and several widgets can update at the same time. We had to extend it. We developed various widgets. We added logging asynchronously via Ajax, both local logging and to Google Analytics. We have a distributed configuration scheme. So the base config is on the server side. We load it with Ajax to the client side, use as a configuration client side, and then the client can override all configuration. It sounds dangerous. It really isn't dangerous, but it's very useful for us anyway. But you don't need to do any of this. Ajax Solr works out of the box, the basic functionality. So this is an overview of our search architecture. You have our website. The only thing we have to do is we have to include our JavaScript library, which comprises 1,700 customized lines of code. That's the kind of work you'll be looking at if you want to adopt Ajax Solr for yourselves. and the Ajax Solar library itself. That's bundled into one minified JavaScript file. We initialize it by some custom scripting to say what facets should map to what parts in HTML. I'm going to show you this more, later. So when you search, for every search you do, and this is important, you shouldn't search directly towards your Solar server. You should use a Solar proxy because of the security issues. You probably heard that lots of times these past 2 days. So when the response comes back from the Solar server, we do logging asynchronously for the user not having to wait. That's also important. Timing is gold for users. And then the results shows up. I'm going to do a demo of this and explaining this further. This is just like a basic overview. So for the site search, the keywords here are widgets and faceting. Faceting is just a special case of a widget. So Ajax Solar allows you to define as many widgets as you like. Everything is a widget. Like a page is a widget, a facet is a widget. You can have 2 facets being the same widgets but 2 different instances of it. The search box is a widget. The result list is a widget. So basically, that's it. So whenever you make a query and you get a response, all widgets are updated without having to reload the whole page. So from some of the facets we developed were like a plain facet. There is a plain facet shipping with Ajax Solar. It's useful, but it didn't quite fit our needs. We wanted to have like to display the facet values and then have a count on them. For the hierarchic facets, we did basically the same thing, but when you click on a facet value, you drill down into the hierarchy, and with that, we did that with a facet prefix. And so the facet prefix determines what you view in the facet, and the filter query filters the query based on what the user clicked on. I'll show it in the demo how it works. We create like drop-down widgets, tag cloud widgets, and the pivot facet widgets. So if you want special functionality with Ajax Solar, it's very flexible. You can do whatever you want. You just have to code it, and it isn't that hard really. So for us, adding a facet it's like the matter of this adds 2 facets, and you have like 6 codes of line, 6 lines of code. Sorry. So I mean, it's really flexible and easy to implement. This is an example of a widget. I'll just skip past it because it isn't that important at this stage. This I'll show in a demo. Pivot faceting. A pivot. This is a definition from the Solar wiki. Pivot faceting allows you to facet within the results of the parent facet. But we don't run Solar 4x, so we had to do this by ourselves. The problem is we have menu facets, and many of you probably have that kind of problem. We have menu facets that shouldn't affect each other, but affect the search results and all the other facets. So imagine here you have 1, 2, 3, 4 different examples of how the main menu on the search page would look like. On top, the top picture, you have the main categories. When you click on one of the main categories, you don't want all the other main categories to disappear. You still want to have the counts there. At the same time as you want to display the counts of all the subcategories within that main category. So that's basically what pivot faceting will do for you. And when you then click on a subcategory, you don't want you still want all the categories to display. So that's kind of tricky to do in Solar, and there isn't a 3.6, and there isn't really an efficient way of doing it. So you just have to tweak your indexing to suit your needs. I'll show you how I did it. Our solution was defining 2 fields. One field for the top-level menu and one field for the sub-level menu. So the top-level menu facet is menu 1, SS menu 1. It just means single string menu 1. And the sub-level is single string menu 2. So when you have those 2 fields, you can facet on them normally. But the trick is to facet on them and facet and filter out search results without filtering out the counts from the facets. So the way you do it, this is on the first example. When you click on a top-level menu item, you tag your filter query that will filter the results. You tag it with a name. Any name will do. As I used here SS menu 1, it could be Acme. It doesn't matter. And then when you do the facet, when you specify the facet field for the top-level menu facet, you just say, OK, let me exclude the tag I used in the filtering of that field. That way, the facet will show the results, even though the search results don't show them. Things get a bit more hacky when you have to do a sub-level query. So this is a second-level query. And you see that I use the tagging and the exclusions. And you can use the tag several places. And all the places you use the tag will be excluded from your facet field. So you see when I facet on the sub-level menu, and I choose higher education, which is under the education menu, I will say when I filter out the facets for the top menu that, OK, don't bother about the filters being used for neither the top menu or the sub menu. So it sounds probably complicated, but it really isn't. If you just sit down and tinker with Solr a little bit. The drawbacks with this, it can be very slow on large indexes. But we have like a small index. We have few unique terms, like very few distinct values on the facets. So it's real lightweight, and we don't see a problem. I tried disabling it and enabling it. Doesn't make a difference for our latency. OK, I'll come back to this later. So the autocomplete. Normally, when you see autocomplete, you get like an auto-suggest function that will just suggest terms for you. We wanted a bit more than that. We want to give our users the feeling that we can read their mind. So we don't want to simply show them terms. We want to show them the documents. We'll suggest documents based on what they're querying. And 50% of our clicks to content from searches actually come from the autocomplete feature. So people don't need to go to the normal faceted search in order to find what they need. They can do it by just using the autocomplete feature. How do we do it? You have to use Ajax. That's for sure. You have to detect keystrokes and send one request to the Solr server per keystroke. This can be a strain on the server if you have like lots of requests, but there are ways to mitigate that. When you receive the results, you just populate a result list. So the techniques we employ in order to make this bearable performance-wise, and we have a response time of like 8 or 9 milliseconds from the Solr server on this, is to have a minimal payload. So the field list you get back from Solr, you should reduce it to a minimum. That's very important, because if you, like us, have big documents with huge bodies of text, it would be crazy to download, because it's a download you have to do in order for it to show on the client side. Like 100 documents with all the text that's in the Solr index. So minimum payload is the keyword here. And if you do have an autocomplete feature like this, where you display suggested documents, you must use the same boosts and query fields as you do in normal queries. Otherwise, they will be confused. They search for lawyer, and the lawyer profession comes up on top of your suggested documents. They press enter, and they come into your regular search. And if lawyer isn't at the top there, it would be strange for them. If you need to group things, like we have several data types. We have professions, we have courses, we have organizations, we have interviews, we have regular articles. You probably want to group the suggestions. So we group them, and you can use that with Solr. With group equals true, you say which group field you want to use. We have like content type. And then a group limit, say like 3. OK, maximum 3 documents per group. Keep the number low, or you will strain the server, and you'll get low response times. Now, the mind reading part, it's difficult, but we have a very domain-specific site. So when people search for something, we can quite safely assume that something is within the title of the document. If it isn't, it will search all the other parts of the document as well, or the necessary parts of the document anyway. But if it's in a title, we give it some special attention. We say that if what the user is entering in the text field is equal, if a title starts with what he's querying for, we give it a high boost. If what he's querying for is within the title of a document somewhere, we don't give it a boost, but we consider it. If the text he's typing is within some other part of the document, we give it a low boost, we count it, but we won't rank it very highly. I'll show you how we define these fields on the next slide. But first, also use caching. Caching is very important, because if the user writes lawyer and then decides to backspace once and write lawyer, then you'd really like to have that lawyer cached. And the browsers will take care of you if you use, for instance, JSONP correctly with jQuery. So how do we define the fields? We have two fields, mainly for the autocomplete. We have a starts with field that will match on fields starting with whatever the user types in the search field. We boost that one higher, because we consider, well, if it starts with it, if it starts with medicine, he probably would like a document starting with medicine, because lots of courses start with medicine, or maybe a profession, being a medicine, doctor of medicine. So what we use is we take the whole field and use the keyword tokenizer factory. So we take the whole field and make it one single token. We replace everything that isn't a regular character with nothing. So we compress the field into one long string of only regular Latin characters. And then we use the edge and gram filter factory to create all variations of all starting variations of the field within the 25 first characters. We don't bother go further than 25, and it's probably too much, because the user will probably never type 25 characters in the search field anyway. For the query analyzer, we do basically the same thing, but we don't apply the edge and gram filter factory. That's important. So this way you get like a starts with filter. That's quite efficient. When you have defined a field, you see how the defined fields part of the XML in schema XML. You just have to use copy fields in order to populate the fields you wish to search on with that kind of functionality. So we use a label, which is our title. OK. Slightly different for the autocomplete function when you search within words, within sentences. This one will match, if you write lawyer, it will match lawyer wherever. If it's embedded in a word, if it's in the wherever it is, it will match it, and it will match law, or year will match lawyer, for instance. We boost it less than the starts with filter. Still using edge and grams. But the trick here is to use it both front and back. You have to specify both in order for it to search in the middle of words, for word parts. You can see from the copy fields that for the starts with, we use titles. For the other fields, we use titles, teasers, and maybe body as well. We have a small index, so it isn't a problem performance-wise. So this is how the autocomplete will look like. When you write, you get a list, and you can click on the list or search further into the categories that appear. So the embedded search basically lets other sites search our data. The same search that we use ourselves. We have two external sites that already use this kind of a mechanism. So it looks like their search, but it's really searching our site or our data, our Solr index. Architecture, exactly the same, with the difference that they can actually override all the config parameters. They can change boosts, they can do implicit filter queries so that they only search in parts of our index, etc. So it's very easy to actually use the search functionality on any website. You just have to include our minified library. You have to specify the skeleton in HTML where things should be, and then use CSS to make it look nice and stay where things should be. Configuration, you just have to initialize the manager. This is pretty much standard Ajax Solar stuff, so read the tutorial. So the feeds engine, what it does is delivering data in bulk to partner organization. We don't care much about getting sorted results. It's for bulk data delivery, data exchange. So we have a RESTful searchable data endpoint that returns XML, Atom. We have one beta partner, which is up and running, and the performance is great. We have response times from Solar, like sub-second for hundreds of documents in bulk, as opposed to crashing the server before. So Solar really works well for data exchange as well. OK, I'll let that hang in there just to move on to how we did with logging. We wrote our own logging backend, a couple hundred lines of codes, really lightweight, because we didn't want to spend money on a huge package, nor spend lots of training on getting up to speed on alternative logging frameworks. So we simply wrote a small PHP log proxy that we call by Ajax whenever you get the result back from Solar. It logs what the user searched, its facets, what clicks he's doing. If he's clicking on a facet, we log it. If he clicks on a result, we log it. We also store all the search results he got on the first page, so you can later analyze and see if searches gain the results they should gain. So obvious why we do logging. We use Google's framework for designing graphs, and it's pretty straightforward. You just do a SQL query, and you get graphs back. So here you can see our searches. It's a spike in the middle of the day. At night, no one uses our site, and the latencies are pretty much stable, around 8 to 12 milliseconds. So you can extract lots of useful information. Most popular keywords not found in the index. Two very important information assets to have, especially the one what they don't find, for us anyway. In our case, it's mostly words that they spell wrong, and stuff we don't normally want in our index anyway, like stripper. We don't have that. So, yeah, I'll just show you a very short demo then, and then. So the autocomplete feature. Now let's hope this works. I'll have to write in Norwegian because it's a Norwegian site. Yeah, we only do it for the autocomplete fields. All the other fields maintain the spaces. But you know, in the query analyzer, we also remove the spaces. So if a user types a space, it's removed anyway. So for the autocomplete feature only. So we don't really need the spaces if the user types. This is information that's stored in the index, which is different from what we index. So we retrieve the stored values directly from Solar and not from the CMS. So that's how we do it. So if the user decides to search for this, you should see more or less. Yeah. So now this is how the pivot facet works. Well, it's really. OK. How do I minimize, not minimize it, but like drag it? No, make it smaller. Make the window smaller. Ah, OK, yeah. I'm going to show you the responsiveness of this. It's not responsive like it's snappy. It's snappy as well, but responsiveness in another sense. You see, like this, for tablets or for mobile phones. That you achieve in Drupal, you achieve it with the Omega theme. Really cool. You should check it out. If you don't use Drupal, use Bootstrap. We use that for prototyping. It's fabulous. Fabulous. Works great for production as well. Hierarchic faceting. I have faceted now on universities and high schools, high school educations. If I want to facet on regions, I can click on a region and drill down. You see here on the top, I remember what I clicked on, so the user knows. All this is quite easy to do with Ajax Solar. You can have lots of facets. You see down here, lots of facets. We tend to put the most important ones up front on top. And if you wish to search now here, the search will only search within the defined filters. So football. Well, no hits. Yeah, OK. So I'm running out of time, sorry. OK, then, that's it.